exam involving 5 and 6, so that's why we haven't seen so many faculty joining us today. And we have 25 poster and second oral presentation. Been very, very dense and a very, very interesting session in the morning for entrepreneurial and building business startup component when you try to come from the laboratory to an industry and develop from there. And then we will have first we will have a section after this in the panel pit. So please join us there.
Reception? A reception?
In the panel pit, joining us there after the talk, and exchange ideas with visitors and you, and have a nice discussion. Enjoy the food. And we will have, after the talk, before we go to the reception, we have to say an award ceremony. The data was collected automatically, so we use a very sophisticated system, and I will make available the data to you so that you can even use this without removing the name of the judges. You can, and the category that you have, you can use this to improve yourself. So after this ceremony, I will send the file to share with you guys. But the last thing we have, I think, is the best component of this gathering, which is the.
Doesn't go that far.
We have Professor Anastasio, the chair of the University of Illinois Urbana-Champaign Biomedical Engineering Department. He's also the chair of the EATA study section. It's my study section. I can't remember the name. That review grant for medical imaging technology by engineering for the NIVIB mainly, and he's the chair of that session, study section. And he, I am amazed by his work. Every time we have to meet every 3 times a year, and he has to keep all this information of grants of different modalities, from optical to ultrasound, which is his main area of research, electrophysiology. He's the one that has to make the final summary of those results in the grant. And every year I might say, oh, he can do that kind of work. For me, it's somewhat impossible. So enjoy the talk, and let's welcome Dr. Anastasio.
Okay, thanks, Jorge, for the great introduction and invitation, and Professor Jung, your hospitality. And I don't know if Gershon is here, but thank him again for nominating me, for suggesting that I should come here. I have to tell you, I really enjoyed my day today, and I can sense there's a wonderful culture here. I can sense there's a community of BME here, and I really appreciate that. It's great. Okay, so let me just tell you a little bit about my research persona, and then we'll get on with the talk. In summary, I'm a computational imaging scientist. So my interest and my work revolves around developing new imaging technologies, as well as improving existing ones. And primarily, I'm interested in the computational and the mathematical aspects of imaging, right? So that could pertain to image formation, solving inverse problems related to image formation like tomography. But the interests go beyond that. We're also interested in theoretical topics in image science, which I'm going to talk about today. How do you optimize the performance of an imaging system? How do you think about even deciding whether an image is good or not? Right? These are somewhat abstract concepts, but we need to have clear understanding of them, especially in the field of medical imaging, if we're going to be designing and evaluating new technologies. We're doing a lot of machine learning for imaging applications, and I'll be talking about that today. And we also are involved in developing some specific technologies, some specific modalities. A couple of them are here. We're very well established in the field of photoacoustic computed tomography. We're doing ultrasound computed tomography, X-ray phase contrast imaging, and other things. We're also doing diffuse optical neuroimaging, developing reconstruction, neural decoding algorithms for that. So we're kind of all over the place, but the beauty of it is, if you have a core set of computational tools, it's very easy to translate them into different problems, especially if you understand the physics. Right. Okay. So today, here's what we're going to talk about. I'm not going to talk about any particular modality. I'm going to talk about some general concepts that arise in imaging science. So in this sense, the talk might be a little bit more abstract than what you might normally expect from an imaging person. So I'm going to start off by giving you my views on how we should think about image quality in the medical imaging domain. Okay. Then the first part of my talk will be talking about using machine learning tools to optimize the design of new imaging technologies. So basically, I'm going to be giving you some insight into how imaging scientists are using brand new deep learning tools to think about designing optimizing systems. And these ideas can be translated to virtually any imaging system. Okay? And then in the latter part of the talk, we'll focus on the problem of image reconstruction using deep learning to improve the ability to reconstruct images from undersampled data. Okay, so let's just start off slow. So I want to give just a general black box description of an imaging system. Right? An imaging system, in essence, is just some sort of a system or device that maps an object property to a set of image data. Right? And you can think of that in terms of just your typical engineering black box diagram: object property in, measured data out. Right? We can think of some concrete examples. In MRI, the object property might be the distribution of proton density within the tissue. Right? The measured data would be samples of its Fourier transform, 2D or 3D Fourier transform. Right? In X-ray tomography, the object property would be the linear X-ray attenuation coefficient. The measured data would be your sinogram data, the set of line intervals to that property, and so forth. Okay? Mathematically, if we don't want to, we don't want to be carrying around these black boxes on our slides, we can just represent it by this operator equation G equals HF. Okay, so G equals HF, and that schematic mean the same thing. Here, G is the set of data that are recorded by your device. F is the object property that you want to image, and H is a mapping. It's an operator that takes your object property and maps it to the data. Okay. All right. So one thing I want to remind you is that image data G that I just showed you. In general, it's not the final image. It's just a set of measurements that have to be subsequently processed to form an image. And that's what I'm showing here, right? So if we define an imaging system, we really can think of it as two pieces. There can be the imaging device, that's kind of the hardware that records some set of data. And then there's a computational engine that takes that data and forms it into an image, right? And that step is generally referred to as image reconstruction, okay? So for example, here's an example, a CT image. So the imaging device records a set of line integrals through the object property, and that image reconstruction algorithm basically inverts that model G equals HF, which might be a radon transform if we're talking about the X-ray tomography case. Okay. The other thing I want to point out on this slide is that imaging systems have many tunable parameters, and this is kind of a real theme of the talk, right? Many tunable parameters. So when we're designing imaging systems, or when we're optimizing the existing systems, we have to have some intelligent way of tuning all of these knobs, okay? And it's not simple. So this is kind of what I want you to keep in mind. Okay. Here's an example. Here I show two slices. These are X-ray CT images through the chest of a patient, right? Through the same section of anatomy, but the parameters that were used in the acquisition and reconstruction were different. The image on the left corresponded to using a thicker slice thickness. On the right, it was a smaller slice thickness. Okay. So clearly, somehow, the image on the right it seems sharper, right? Better resolution. The image on the left seems lower resolution. But maybe I can just ask you a question. I mean, which one of these images do you think is better? Let me pick up some idea.
Better for what?
Better for someone said better for what, right?
Yeah.
Thank you. That's exactly what I'm looking for, right? So when we define good, we need to define what the purpose of the image is. Okay. So if it were me, if it were someone in my family getting the scan, I'd say the image on the left is better as long as that image quality is sufficient to accomplish the intended diagnostic task. Because the image on the left involves a lower radiation dose than does the image on the right. Okay, so do you see now it's complicated. When we define good, bad, there's a lot of factors that have to come in. We have to specify diagnostic task, we have to specify observer, and we have to consider all sources of variability. So let's talk a little bit about image quality following up on that idea. Somehow we need a figure of merit that summarizes image quality if we're going to try to optimize an imaging system or design a new one. Okay? Image quality metrics can be divided into two broad classes. One class is generally referred to as the physical-based image quality measures. Those physical-based measures of image quality might be the things that you normally think about, such as kind of the resolution of the image, the noise level in the image, signal to noise, contrast. All of these measures are just based on the physical or statistical properties of the image. Right? On the other hand, we could think about objective or task-based measures of image quality. And these, as I'm going to talk about in a moment, go beyond the physical measures because they take into account the issues that we identified in the last slide. Right? So let me just quickly show you a few limitations of these physical-based measures of image quality. These are just some simple toy problems. On the bottom, these are just some noiseless images created on a computer of some uniform disks of various radii. And what we did was we added noise to these disks, and those are shown in the top row. And the contrast to noise ratio in all three of those images in the top row is actually identical. Okay? But do you think that the detectability of those disks is the same to you in all these images? No, they're not, right? Obviously, this big disk we can still spot it easily, even though it's embedded in noise. Where that small disk on the far left, that's embedded in the noise, right? Even though the contrast to noise ratio is the same. So this is just a reminder, okay, well, contrast noise ratio might not be a good summary measure of image quality if we're trying to detect tumors in images. A similar situation here, mean square error is commonly used in the image processing literature. Again, it's not really great for assessing medical image quality. So here, the image in the top row on the far left, let's say that's the original image and it has some small tumor embedded in it, indicated by the arrow. These other 5 or 6 images, the 5 images, were formed by perturbing or adding noise to the original image. They all look very different. They all have the same mean square error measured from the original image. Okay, again, that's very misleading. You see the image processing literature, people use MSE, peak signal to noise ratio. These measures they all without blinking. In medical imaging, we blink a lot before using those, right? Because they're not useful. So that brings us to the objective or the task-based measures, right? So in the field of medical imaging, these are what are really advocated, right? So if you send a grant to the NIH developing or evaluating an imaging technology, they're going to want you to think this way about image quality. Okay? And these task-based measures have the ability of an observer to perform certain tasks or certain statistical inferences. Common examples would be signal detection or parameter estimation. So in other words, in this view of image quality, we're going to specify an observer, and then we're going to measure image quality based on how well that observer achieves his or her or its goal on a set of images. Okay. So in order to assess image quality in this more comprehensive way, we need to know a lot of statistical information. So it's not easy to do. All right. Specifically, we need to know what all the sources of randomness in the image data are. And this is something that we're going to be talking about for the first part of my talk, right? And there are really two obvious sources of variability in image data. One is the measurement noise, right? Just like in any measurement system, in an imaging system, there's measurement noise that gets added during the acquisition process. Another source of noise or variability that may not be quite as obvious to you has to do with the distribution of the objects to be imaged themselves. Okay, right. So when we optimize an imaging system, at least for diagnostic applications, typically we want the imaging system to perform well on some cohort or some collection of people. Right. So let's say we're going to image all the brains in the room now. Right. We want to optimize the imaging system to perform well, imaging all of your brains. Well, I mean, all of your brains are slightly different size and shape. They're not identical, right? So basically, you can imagine that your brains represent some ensemble, and there's really some probability distribution that describes these, where if I drew a sample from this distribution, I get one of your brains and so forth, right? So this is what I mean by variability of the object. It has to do with the variability in your brains. And the stochastic object model is a way of actually capturing or describing that source of anatomical or structural variability. Okay? And this is generally very difficult to quantify. And so this is a challenge for imaging science. How do we quantify that source of variability? And once we do, then we can actually go ahead and optimize and compute task-based measures. Okay. So often when we are first designing new imaging systems, often it's convenient to do this in silico. Okay? If we have the ability to have a numerical model of our imaging system, it can be very convenient, right? Because we can explore different data acquisition designs, different reconstruction algorithms in a very convenient way that you just wouldn't be able to do if you had to build each one of them. Okay? So this is something that we commonly do. But again, if we want to optimize a system design, even if it's in silico, we still have to use the meaningful measures or figure of merit to design to guide our efforts. So we're still going to need those task-based measures, which means we're still going to need a stochastic object model to capture in a meaningful way the anatomical variability in the cohort of people or things we want to image. Okay. Here comes the deep learning. Okay, so basically I said, basically I just gave you a course intro on theoretical image science just now. So now we're going to talk about using state-of-the-art deep generative models to do what I just said we wanted to do, right? To establish a stochastic object model. So before I go on, I should have done this at the beginning. I mean, how many of you guys in the room are using machine learning methods in your research or have some knowledge of them? Okay, surprisingly few. How many want to use them in your research? Okay. Oh, okay. I was expecting more. in my home department, everyone's on board. Okay. Well, that's fine. So let's talk about how we can actually learn a stochastic object model. And we're going to use this class of deep neural networks that are called generative models. Okay. Generative models are a class of deep neural networks that can actually learn a statistical distribution from a collection of images. The idea is that this, I think it's a laser pointer here. This generative model here, this is a deep neural network, and we don't need to worry about what's inside that box. Typically it has a bunch of layers, a bunch of convolutional layers, and nonlinearities, and pooling operations, and all of these things. We don't need to worry about it. The point is, this is a neural network. The input to the neural network is that vector Z. That vector Z is drawn from a random distribution, let's just say a normal distribution, zero mean, with some variance. And the dimension of that vector Z is relatively low dimension compared to the dimension of our image. And the goal of the generative model is to basically take an input, a vector Z, and at the output produce a sample image that's drawn from some distribution that describes the ensemble that we want to image. Okay? So the goal here in deep generative modeling is how do we train that model so that we can learn how to create images or images of objects that are realistic. And there's a specific type of generative model called the Generative Adversarial Network, or a GAN. And this is really state-of-the-art in the deep learning community as far as generative modeling. And again, I'll just take things slow here, but let's just look at the schematic here on the right here. This is the generator that I just showed you on the last slide. So again, the point is, this thing's a neural network. It's some random noise vector, and if we train this thing the right way, the output's going to be an image that's representative of the ensemble of images that we want to image. Okay? So the trick is, how can we train this network? I mean, think about it, it's kind of remarkable that you could train a neural network to take just a random noise vector and then map it to something that looks like that. Right? It's kind of remarkable. And to be honest with you, this couldn't have been done a few years ago, literally. So this over the past few years, this field has just come up, and it's just affecting all aspects of imaging science. So to actually train that sort of generator, that's where this GAN comes in. And there's a process called adversarial training, where you have a discriminator, you have a generator here, And basically you pit the discriminator and the generator against each other, and they're trying to outsmart each other, essentially. They're trying to solve a min-max loss, and they're trying to outsmart each other. And if you train this in such a way that you reach an equilibrium, then when you're done, you take the generator, you rip it off, you put it here, and now you're ready to go. That's the short version of the story. Of course, there's all types of black magic details behind that we won't go into now, but happy to talk to you later. The other thing I should point out here is this generator, this neural network mapping, we'll denote it by that function g of z. Okay, so z is the input. We give it a z, and it outputs an image. And I've also shown an argument theta g there. That theta g denotes the weights of that neural network. We'll make that later. Okay. So that's right. GANs are great, but if we're trying to learn the distribution of objects, the noise distribution, we just want to learn, for example, there's variability distribution. We just want to learn, for example, there's variability in your brains, right? We're trying to capture that variability, right? But as I mentioned before, there's at least two sources of variability in the images, right? There's variability due to brains are different, and then there's variability due to noise is added to each of these measurements. We want to separate those because I'd like to learn just the variability in the distribution of your brains. So we need a different type of GAN, right? And luckily there's a way to do this, and it's called an ambient GAN. And the basic idea is here. It's very similar to the traditional GAN that I very briefly introduced you to. The only difference here is now we introduce this measurement operator H into our pipeline here, right? So the idea is as follows. Assume that we have access to a collection of experimental measurements. So if we're talking about MRI, that would be the raw case-based samples, right? So let's say I have the raw, each of you gets an MRI scan done of your brain. And let's say that I have access to the case-based data, okay? Then what we do is from this collection of case-based data, we're gonna want to learn a generator that produces images such that when we put them through a simulated imaging system, it produces case-based data that are indistinguishable from the case-based data that we actually measured from you. Okay? So in this way, we can learn the distribution of objects from knowledge of indirect measurements from the case-based data that we actually measured from you. Okay? So in this way, we can learn the distribution of objects from knowledge of indirect measurements of those objects. So this is the magic of this ambient GAN. So for imaging science purposes, this suits our needs perfectly. So I'm going to talk about now an implementation of this that one of my students, Wayne Min So, recently developed, and it seems to work wonderfully well. Okay, and here's just an example using X-ray radiographs to make things a little bit more concrete. So let's look at the image on the right. This is an example of what an X-ray radiograph might measure, right? So you see a bunch of anatomical structure, but if we zoom in here, you can see that clearly there's noise there too, right? Of course, right? So if we trained a traditional GAN on these images, we'd be learning the anatomical variations in the population, but we'd also be learning this noise I don't want, okay? Here's an example of what a noise image would look like. So this measurement, this measured image, you can think of it as taking a clean image, adding noise to it. So we want to train a GAN that will give us the distribution of those clean images. Okay? That's basically what I tried to tell you on the last slide. So hopefully this makes it more clear. So so there's a type of ambient GAN called a progressive ambient GAN that we developed. And here's an example of what we did. So if you take a conventional GAN and you train it on the original noisy images, and then you synthesize an image, you get something on the left. So you see there's noise there. If you apply this ambient GAN, and then you synthesize a new image, you get this image. And if you zoom in, you can see there's most of the noise is gone, right? So that's just showing that we can actually do what we want to do. Okay. So this is interesting. So some of these images are real. These actually are the actual chest radiographs. Some of them are fake images that were produced after the ambient GAN was trained. Right, because after the ambient GAN is trained, we feed in random noise vectors, we get out example images. It's not obvious. Okay? It turns out, yeah, the ones in the box, these are the actual fake ones produced by the GAN. But this is just giving you a sense that, okay, yeah, these new technologies, they can actually learn the statistics of images well enough that they know how to produce fake ones that look good. Right? So they're not just learning the second order statistics, they're learning some higher order statistics. We actually don't know exactly what they're learning, but we'll talk about that later. Here's another example where this has to do with MRI, brain MRI, to go back to the example. right? So imagine we're doing brain MRI, and here's, let's say, the 2D K-space plane that has noise in it, right? So again, we already talked about this example. So if we put every one of you in the scanner, and if we measured the K-space data, we gave it to me, you know, each of your K-space data would look something like that, okay? So the goal is, from knowledge of only these noisy indirect measurements, we want to train again. Yeah? And again, here we go. Some of these are actually real MRI slices, and some of these are fake ones produced by the GAN after we trained it using that ambient strategy. Not obvious, right? These are the fake ones. Pretty good. This is just an example of showing how when you're training the GAN in using the adversarial process that I briefly mentioned, this is showing what the synthesized images would look like at different points in the training process. So it just shows you that, you know, as the training progresses, you're able to synthesize images that look more and more realistic. And this is where all the technical know-how really comes in, and how to train these things stably. It's not a trivial thing, unfortunately. In terms of trying to understand a little bit more what was learned and whether things make sense or not, we actually computed some histograms of structured similarity metrics, or SSIM metrics. So the SSIM structured similarity index value, this is just a measure that describes how similar two images are, essentially. So what we did was we took the experimental real images, right, and we randomly took pairs of them, we randomly sampled pairs of them, and then computed this SSIM value, and then created the histogram. That's the histogram on the left. Then we did the same thing, but we did it with the synthesized images, the fake images. We randomly took pairs of the fake images, computed these similarity index, created a histogram. And then finally here, we randomly took a real one and a fake one, and did the same thing. And you know, this is still just an intermediate validation, but the shape and structure of those histograms is similar, which is, you know, at least I would say, you know, it's a necessary condition. I don't know if it's a sufficient condition, but it's reassuring. Here's another example. Of using the ambient GAN, but now on a stylized X-ray CT example. Okay, so consider that we have an object distribution that represents the linear X-ray attenuation coefficient, and then we have access to what the tomographic projections are, the radon transform values. Okay, and then there's noise added to this. So here's a collection of fake images mixed with the real images, and they look pretty good, suggesting that the ambient GAN did a good job of learning the statistics in the collection of images that we trained it on. Okay, so that's kind of interesting. So now I kind of proved to you that we have the ability to kind of learn the statistical properties that describe anatomical variations in objects, right? And once we have that, and if we know the statistics of the noise, now we kind of have the statistical information we need to move forward and compute figures of merit of image quality that then can subsequently guide optimization of the imaging system acquisition or whatever. Okay, so I'm just going to talk very briefly now about kind of what the next step might be in terms of using deep networks to assess image quality measures related to signal detection. Right, so this might be relevant if you're trying to detect a tumor in an image, for example. If you wanted to optimize an imaging system to work well for tumor detection, you know, you would compute figures of merit following the procedure that I'm about to show you. Right, and then for those of you who are not familiar with convolutional neural network, CNN, essentially this is one of the popular types of deep networks that work well on image data. Okay, and the idea is that the input of the network, you feed in an image, and then it goes through, the image is fed through various layers where features of various levels of abstraction are computed. And at the end, we have a few scalar output values that we can relate to posterior probabilities. Okay. And what I want to consider here is actually not just a simple detection task, but something a little bit more interesting. It's a detection localization task. So basically, the situation here is that the equation on the top just describes our image. We have G equals HF plus N, right? So G is our measured image, F is the object, N is the noise. Okay? And we're going to consider the situation where there could be a signal present in the image, okay? Or maybe there won't be. Some of the images will be signal absent. Some of the images will have signals in them. And for the images that have signals in them, they could actually be positioned at L different locations in the image. So the task we address is make a decision as far as whether there's a signal present in the image, and if there is a signal present, tell me which of the L locations the signal is at. We want to compute a figure of merit for the CNN-based observer for this task. And again, this has some medical relevance. This is just kind of a schematic showing our simulation study relevant to what I just told you, right? So basically, on the left-hand side, this is our measured image, which can be thought of as some background, right? Plus a signal, which could be at one of, in this case, L equals 9 locations. And then, of course, we'll add noise, right? And then in some of the images, there won't be any signal. And the idea is we're gonna compute a bunch of these images. We're gonna train a classifier. Then we'll evaluate the classifier on a test set and compute the measures of performance. Detour into signal detection theory. There's a rich body of literature related to signal detection theory that goes way back to the middle of the 20th century or before. And there's something called the Bayesian ideal observer. And the Bayesian ideal observer represents a detection strategy that is optimal. Right? So basically, no classifier can be better than the Bayesian ideal observer. Okay? And when we can approximate this, we would like to do it because it will it'll basically tell us what the maximal amount of task-specific information is in the images. However, it's generally difficult to do. However, if you have a CNN, then there are methodologies out there for doing it, and we published a paper on that last year. This represents what the ideal observer decision strategy would be. Basically, I don't want to belabor this, but basically the strategy is you compute these ratios of posteriors. H sub j represents the different classes. You compute these ratios of posteriors. You figure out which one is maximum, and then you form a test statistic, compare it to a threshold. Okay. I guess the thing I do want to point out here is that, okay, yes, this theory, this math exists. It's existed for a long time. I guess the reason I have this slide here is just to tell you that these probabilities can be estimated by those CNNs if you train it the right way. So you can train a CNN, estimate those probabilities, and then you can basically plug into signal detection theory and try to approximate the ideal Bayesian observer. It's kind of cool. So here are examples. If you do what I just said, here are examples of localization ROC curves, where on the x-axis, this is the positive fraction. On the y-axis shows the correct localization fraction. Okay. So this is a way of summarizing the performance for an observer performing that detection localization task. Right? And if you wanted a single scalar figure of merit, you could take the area, you could fit these, and you could take the area under these curves. You'd have a single scalar figure of merit, and then you could use that to guide the optimization of acquisition parameters or systems in some way. That's kind of short version of the story. Okay, so you're probably tired of quality by now. So maybe we'll go to image reconstruction. I think so. This is a different way of using deep learning. Does anybody in the room, anybody work on image reconstruction or have familiarity with inverse problems? Mostly no, though. I see people looking around like, oh my God. Yes, okay. So I was going to walk you through this very quickly, and again, I'm not going to go through a lot of details because I know that it may be outside your area. But let's start off with this equation G equals HF plus N, which you saw before. Okay, G is what we measure, F is what we want. That's bottom line in any holographic system. Okay, so somehow we have to invert that equation, right? And we're going to consider the situation where this is, let's assume everything's linear. We have a linear system here, and let's assume that this linear system is underdetermined. Okay, which means we have fewer measurements than we do unknowns. So this would correspond to a situation, for example, in MRI, where you're undersampling intentionally so that you can reduce the acquisition time. So if you want to speed up your imaging, one strategy for speeding up imaging is just acquire fewer samples, right? But if you acquire fewer samples, now you've got an underdetermined system. So now, okay, so you've solved one problem, now you have another problem. Okay, how do I invert an underdetermined system, right? So this is what we're going to talk about now, and I'm going to give you just a glimpse into one way of using deep learning for this. Okay, this is a traditional approach for regularization that's used widely in the field of medical image reconstruction. This is an example of a penalized least squares estimator. Right? So we have basically some function here that we form, and then we minimize it, and we define the solution to our inverse problem to be a minimizer of that objective function. The objective function contains two pieces. The first term is a data fidelity term, and the second term is a penalty, which can be related to a prior that describes some properties of the sought-after solution that we believe exists. Lambda is just a scale. Right? Some of you may have heard of like compressive sensing and using sparsity as a tool for regularizing inverse problems. Well, that plugs into this prior feed. So if that's an L1 norm, then you're doing essentially compressive sensing. So here's where we're going. Okay, this is well known. What we're going to do now is we're going to instead of trying to handcraft this penalty phi, we're going to use deep learning to constrain the problem in a different way. We're going to try to learn our way out of having to manually specify that penalty function phi. Okay. And to get the idea, let's just consider a simple case where there's no penalty. On the top, I just have a traditional least squares problem, right? So basically, the top equation is saying, okay, I want to determine an object f such that it produces measurements that are close to the measurements g that I actually acquire. Okay? Nice thing about this is it's convex, we can easily solve it. Bad thing is that if we have a severely underdetermined system, so if H is rank deficient, then it's not going to work so well. Okay? So what we can do now is we can actually replace that top problem. Okay? So what we can do now is we can actually replace that top problem with where this function g, this is that generator that we talked about in the first part of the talk. So we've replaced f in the top problem by this generator g in the second problem here, okay? Because remember how the generator g works. If we feed in a random vector z, then g gives us an object f, right? So now notice instead of optimizing over f, we're optimizing over the latent space z, which is a lower dimensional space, okay? So there's some good things and bad things here. Good things is that, okay, well, if we've learned G well, then solving this problem guarantees that our final solution is going to be in the range of G, right? It has to be, whatever image we reconstruct has to be producible by G, right? That's why we do this, right? So G is serving to constrain the solution space. There's no free lunch. Bad thing is now we have a non-convex problem, and basically, if you're not familiar with this, what it means is it's harder to solve and we don't have nice guarantees. Like we did before. But let me show you that it's still useful. Some other limitations of this technique, which I'll refer to as CSGM, are that if that generator G is not trained properly, then we may have what's known as representation error. It means we may not be able to actually recover an object that's consistent with our data. That wouldn't be good either. Okay? So I'm going to tell you a way around that too. And here's just kind of a schematic of where I thought. Let's start with these pictures on the bottom. Right? That model error thing that I just talked about, that's depicted in the schematic here. So this is a 2D plot. Let's just assume we live in a 2D world. And the image that we want to recover, f, is just a 2D vector. It has two components, f1, f2. So f1 is on this axis, f2 is on this axis. So this shaded area here, this shows the range of G. So basically all of the objects f that can be produced by our generator have to live in here. This line here shows the set of objects f that are consistent with the data. Okay? So because this blue shaded area doesn't touch this line here, this is showing that we have that model error that I just told you. This is bad for medical imaging. Right? We never want to use that because it would mean that if a patient had a tumor, it could potentially be missed. Right? I mean, so it would be just irresponsible actually to do that. But by the way, it's happening all the time in the research period. So what we want to do is we'd like it if we could adapt the generator to kind of expand its range so that we can have data consistency and get rid of that model error. How do we do that? We modify our optimization problem. Instead of just optimizing only over Z, now let's optimize over the weights of that generator and give it some flexibility to expand and be consistent with the data while still enforcing prior knowledge about what a sensible image should look like. That's kind of the bottom idea. So this new technique we call IGAM. And one of my students, Saitan Badra, recently described this work at the SPIE medical imaging meeting. If we want, we can add a penalty to this too. I don't want to belabor this point, but we can take that IGAN method and we can add a penalty here. For example, a total variation penalty. You don't need to worry about that. But the point is we can do other things to even improve image quality. And to solve this problem, we can use standard tools from deep learning. So if you download TensorFlow, you have access to all these stochastic optimizers. Those stochastic optimizers you can use to solve these things because they're generators, differentiable, and so forth. Okay, so let me show you. Let me just show you some numerical studies. This will give you some sense for how these things work and how they don't work, right? It's also understand when they don't work. So we're going to consider a stylized MRI experiment, and let's assume that we have multiple coils, and those of you who work in MRI know what I'm talking about. If you don't, it doesn't matter. So we're just going to have H, which is relevant to MRI, which means it's somehow related to a Fourier transform operator. And we're use the there's an open source data set at NYU called Fast MRI. So we used data set from there, and we trained again using those images. And the data set contains MRI knee images as well as brain images. Okay. And the sampling pattern, the case-based sampling pattern that we considered was random Cartesian sampling with an undersampling factor of 4, which is actually not very aggressive. We compared this IGAN machine learning-based method. We compared it to a traditional penalized least squares method with a TV penalty. So that's a classic non-learning based method that works well usually. And then we compared it to that first method, that CSGM method. And this is just some more details about the MRI experiment. The images were 256 by 256. There were 12,000 of these knee images that we used to train the GAN. 15 coils were assumed, and we had access to a ground truth image, so we could compute error maps. So here are some examples on the top row. These are examples of the actual images. These are the actual MRI images that are in the database. Okay, and then at the bottom, these are images that were synthesized using the GAN after we trained it. So again, it somehow seems kind of sensible. So here are some results of images reconstructed. After we simulated the case-based data and implemented those reconstruction methods, here are some examples. On the far left, that's the ground truth of sliced through the knee. Okay. The second image is this classic, this PLS TV method, the non-learning based method. Here's the CSGM method that's susceptible to that representation error I talked about. Here's the adaptive method that's supposed to do better than that guy. And here's the IGAN method with that extra TV penalty included. Okay. And the bottom row, these are error maps. So basically, it's a difference image between the reconstructed image and the ground truth. Okay. So you can see on the PLS TV, you can see structures in the error map representing errors. In the CSGM, you can see a lot of structure there due to that representation error. And the IGAN, even without the TV penalty, worked pretty well, at least in terms of the error level. Okay. And here are just some zoomed in regions, and we have just some preliminary image quality scores. So at the beginning of the talk, I badmouthed PSNR and SSIM. But I'm just doing it here as a preliminary measure, and you measure to find the preliminary measures. But again, the adaptive GAN method, it outperformed the other ones. So one final thing that is really interesting that again you don't see a lot. I mean, whenever people publish a machine learning based reconstruction method, which is happening all the time now, it's kind of or he's shaking his head. They write the paper always expecting that the conclusion of the paper is going to be this is the best algorithm in the world, right? And I don't think that's operating in good faith. So often what happens is that when you train these machine learning algorithms on a set of data, they'll perform well. But then if you happen to apply them on data that are far out of distribution, that are very different than the data you trained it on, weird, bad things can happen. Okay? And again, if we're talking about medical imaging, doctors don't want to deal with that possibility. We need to have robustness. We need to be able to trust our images. Okay? So here I'm going to show you a simple study where we actually investigated this. And the way we did it was, we did it with these MRI images again. We trained our GAN initially on a collection of P1-weighted brain images. And then when we implemented the reconstruction method, we did it with data corresponding to 3T images. Okay? So this represents some sort of domain shift, right? So there's some weird thing should happen, and indeed they did. Here are some examples of just what the images look like. On the top, these are the 1.5 Tesla MR brain images, and here's examples of 3T images. So you can see just in terms of the intensity range values that there's differences. There's differences there. And here are the reconstructed images. Again, left column is ground truth. Second column is that conventional non-learning based method. And then here is the CSGM method that has that representation error problem. And here's the adaptive GAN method. And so the take-home points here are that the CSGM method really has severe problems, right? So as soon as you applied it to an image that was to data that corresponded to out of distribution, I mean, the thing falls apart. Luckily, the adaptive GAN method can handle that in some. Non-learning method, it's blurred a little bit, but it doesn't fall apart, right? So this is just a reminder that kind of non-learning based methods, generally they don't fall apart. Like they're non-learning, so there's no in distribution, out distribution. Well, machine learning methods may or may not fall apart when you apply them to different types of images than the ones they were trained on. And so this one suggests that there's robustness of the IGAN method, but still, use of these methods in practice should engender skepticism, and we should be careful. I'm not saying they're useful. I think they are useful, but we need to be careful. So I think it's a good time to end. So I just gave you a partial glimpse into some of the things we're doing in my lab. And just to remind you that deep learning is having a really large impact on really all aspects of biomedical imaging. And I mean, clearly people are using deep learning for post-processing tasks like segmenting structures in images, detecting structures in images, removing noise from images, improving the resolution of images. Deep learning is used all over the place for that. But what I showed you today is deep learning is also being used kind of underneath the cover, so to speak, for the more abstract tasks such as assessing task image quality, optimizing imaging systems, and image reconstruction. And in my lab, we do a lot of this type of work. So I think I'll just end there. And let me just thank Wei-Min Zhou. He's a fantastic student who did all the ambient GAN work. And Sai Tambadra implemented the MRI-based reconstruction methods I showed in the past, in the last part of the talk. So with that, thank you so much for having me, and I'll be happy to take any questions.
This ground truth image, how do you know that that one's correct and that that one is actually teaching your deep learning method the correct way to identify discrepancy or image, blurriness or whatever it might be?
Right.
The correct way to identify discrepancy or image, blurriness or whatever it might be.
Right. So that's a great question. So here, the ground truth was used just to kind of assess the quality of, I say quality of quotes, of the reconstructed images, right? So here, there's no problem because these were all based on computer simulations where we know by definition that's the ground truth. And this is one of the valuable things about doing computer simulations when you're trying to understand a new system or a new reconstruction algorithm because of exactly what you said. Right. In practice, if you wanted to use experimental data to validate a reconstruction algorithm, like an MRI, for example, you could always acquire densely sampled, fully sampled case-based data, that satisfied the Nyquist condition, where you have a full rank, where G equals HF is full rank, and you invert that, and that would be very trustworthy, but still there would be noise in there, so it would exactly be ground truth.
Thank you so much. So a couple of questions that I had. First of all, for the regularization schemes that you mentioned about the phi function that you use, have you looked into how Loretan, S-Loretan, the regularly used ones are performing in comparison with what you had? That was my first question. And the second question that I had was in finding the differences between the ground truth and reconstruction version. So you used looking squared. But wouldn't it be better to use, let's say, RDN and MAG measures so that we both have the magnitude and also the changes in the structure of the images?
Sure. So for the second question, yeah, I mean, Yeah, I mean, MSE or RMSE, I mean, yeah, we're not a defender of those. It was just convenient and just for very initial evaluation, you can use those, but it should definitely, it's not the end, right? And ultimately, I mean, if I'm gonna take my own medicine, ultimately, we should do some sort of task-based quality assessment. So I would only say that reconstruction algorithm A is better than reconstruction algorithm B if I specify a particular task and I specify an observer. And I can say something that has some sort of meaningful clinical value, right? Otherwise, it's just valued. It's just a paper in the processing journal, right? And then the first part, you're asking whether you compare it to conventional methods with different penalties. Is that?
Yep.
Sure. Yeah. I mean that's being standard, and that's exactly why we compare it to a PLS-TD method, because that's sort of one of the very competitive methods. It's a compressive sensing type method that exploits gradient-based sparsity, and so yeah, that's exactly why we did that. And we always sweep the regularization parameters. That's when there are regularization parameters, then it's another thing you need to be careful
Yeah,
about.
the microparameter.
Yeah.
So, and you mentioned many different techniques. Is there any conclusion that you can make that for, let's say, MRI data, this type of regularization works better, or for the other type of data, the other works better, or and maybe the related question is, when you want to compare the images, would you do any co-registration of the images before you do any comparison between them?
So no, I mean, in general, no, right? I mean, because if one of the images is shifted, then it's wrong, right? So I mean, but ultimately there should be a series of evaluation steps that start from very naive cases, just making sure that you're solving the optimization problem that you thought you're solving, all the way to ultimately task-based things where you're considering specific tasks and then making statements about the value of different algorithms based on those measures. So, but these are good questions, and these are just a great reminder that it's not easy, right? It's not easy to be fair and systematic when you're creating complicated computational systems like this. But it's really important, at least in the medical imaging field, it's really important if you want our work to have impact.
Thank you.
I have a question about one of the last mathematical models you showed. Only the last mathematical model had a value for eigenvectors, the eigenvector of the system. So how likely are your mathematical models to show to be non-convergent just on the stiffness of the system?
So I'm not sure I understand. I mean, so is there a particular slide that
Yes. I got it. It's, I think, the last one before image reconstruction.
Oh, the last one. Oh, I see. Okay, let's go up here.
Yes.
They're like this, or okay.
You have the value, the second F, you said is for the eigenvector of your initial.
Oh no, I didn't say eigenvector.
No.
No.
Yeah.
Yeah. No, I mean, so no, I didn't interpret this in terms of eigenvectors or similar system or anything. You could, but I mean, but it didn't. But I mean, if your question has to do with whether you can actually solve this or not, is that fundamentally
Yes.
the question is?
Yes.
Right. I mean, that I think is that. Yeah, you should ask that, right? I mean, anytime you have a non-convex problem, by definition, non-convex problem means that you have a function, you want to find the minimum of it, but there's many local minimum, right? So there's no guarantee that you can land in a global minimum. You might land in a local minimum. And the question is whether you can live with that or not. So one way to deal with that with these, and this is something that's done in deep learning all the time too, is that you'll choose multiple random initializations of the model, and then you'll solve this problem, and then you'll figure out which of them most likely landed in a good local minimum, which I agree that's kind of the first kind of distasteful. And we have ways around that I talked about today. But yeah, I mean, like I said, I guess I can have one general comment here. So I mean, if you start off with that PLS-TD method, right? Which works pretty good. I mean, I think I showed you. That's a convex problem, right? We understand it. We can solve it. We don't have to stay up at night worrying if we landed in a bad local minimum. Okay? When you go to these deep learning-based methods, I mean, in my opinion, the only reason to go to them would be if you're in a regime where you're so data limited. If you're so, for example, an MRI, if your case-based samples are so sparse that compressive sensing or the PLS-TD method are not working, and then if you're greedy or desperate, then you'll say, okay, I'm gonna trade off this beautiful convexity and peace of mind for this thing, which is not convex, but uses a stronger prior. And it gives me hope of actually solving a problem with fewer data. So there's that trade-off there, right? So I wouldn't want to solve a problem like this if I had a lot of data, right? I mean, I'd solve a convex problem like use compressive sensing or something like that. But if I'm desperate and you know, I'm willing to live with the non-convexity, then this opens up new ways of thinking about the problem.
I have one question. So this regularization problem have been linked to the Bayesian formalism, which were typically what you're doing is introducing a kind of posteriori distribution for your function. And the typical way is to assume Gaussianity, and then, for example, if you are in a minimum norm, what you're asking is second derivative. I mean, when you're in the rate or whatever other function, you're asking second derivative to be smooth, or you're asking the minimum norm to be smooth, or the L1 to be sparse. But at the end, you have an interpretation from the probabilistic point of view.
Yeah, that's right.
So is this new, what I call eigen, moving us to a nonlinear, non-Gaussian family of functions?
It is. It's exactly. So you can definitely interpret all this in the Bayesian framework. And I mean, I didn't talk about it today, but there are some new classes of generative models that are different than GANs. They're called flow-based models, and there, I mean, you can actually evaluate the likelihood function. So they're literally you're learning a PDF, right? So I mean, you can essentially connect it to the basic framework. Basically, the log of that PDF is what you think of as normally the penalty and penalizing this very problem. So yeah, it is basically opening up avenues for learning more informative projects.
Non-parametric estimation of data. So you would need a lot of data to
Thousands of but it's surprisingly you don't need millions like the computer really does, because the medical images have certain structure which seems to help.
So how many training sets did you use?
So it depends on the problem. Typically either 5,000 to I guess right 15,000 here in terms of those MRI slices, which was actually surprisingly low. I mean, so. But again, you know, but the claim is we're not sure. I mean, certainly we're not accurately learning the full PDF, right? Even though it can synthesize images that look good. I mean, there's almost certainly at some point we're not accurately learning some of the higher order statistics. So this is an active area of investigation in our lab, and also more broadly in the machine learning lab, is trying to understand what these generative models are learning and how to validate them. And again, in my view on this, in terms of medical imaging, if we want to validate them, I go back to the first part of my talk. I use the objectives and past-based analysis. If the generative model learns statistics that I need or the doctor cares about, then I call it a win, even if it doesn't learn the full PDF. But this is an open area.
So one last philosophical question here. So according to many experts, we are getting into this new winter period for the machine learning. So what kind of ideas and innovative ideas can take us away from that trend?
Oh, that's interesting. So I mean, we should turn off the camera. But really, no, I mean, honestly though, I mean, in the medical imaging field, I think one thing that we need to do that I mean, I feel like it's a grumpy old man, but I mean, be more careful when we evaluate things. I think we can't just keep publishing paper after paper without carefully evaluating them, because the SNR of the literature goes down. So at least in the medical imaging field, when we publish a new deep learning-based recon method, we should evaluate it in a careful way for specific tasks. We should look what happens when we apply it to our distribution data, and we should try to make some argument that this thing might be useful. I think if we do that and we're responsible, then I think it'll be healthy for the field. Because otherwise there will be a dip, and I'm not sure what will happen.
Okay. So what about get rid of this rigid scheme that is this cognitron introduced by Fukushima a long time ago? That is the basis of all. That is the principle of all deep learning. We think we know enough about neuroscience that we can get.
Oh, I see. So that's I mean, if I understand where you're going, I mean, that's a whole other avenue. It's just having more informed network design from better understanding of neuroscience. And of course, that I mean, we still can't compete with what nature gave us. So I mean, that's intriguing.
You had a question to that.
Go ahead.
No, I have really not.
Okay, so one kind of fundamental question that I have, maybe it's because of my lack of understanding of it. So when you're forming the generator, right, isn't it like inherently solving an inverse problem over there to kind of find the kind of like H matrix so that you can form a generator, and then you're using the generator to basically reduce the problem from being an underdetermined problem and finding a hyperparameter to basically use a generator and solve the problem. So is that kind of convoluted in that sense?
I mean, so here, this are you talking about this H here? I mean,
Yes.
So
I mean the G that you're so in the last slide slide that you were showing before, so instead of having the phi function, so basically you were using the G function in order to solve the problem kind of easier, because I assume the system is going to be full rank and you can't easily solve it.
Well, it won't be full rank.
It won't be, right?
Yeah, no.
Okay.
Well, I mean, if it is, you shouldn't be using that method.
True. But what I was asking is, so in forming the generator, isn't it inherently you are kind of have to solve the inverse problem as well to be able to find the generators? Or
No. So basically, I mean, the idea here is that learning the generator, learning that distribution of objects, that has nothing and should have nothing to do with the energy system or the infrastructure layer. That's just a property of the object distribution that you want to learn. That's the prior information you want to learn. You want to bring it into your inverse problem to somehow constrain
that's the
it.
priori information.
Okay.
So my general question was going back to this morning or earlier we heard Jared give a presentation, right? So in his presentation, when he was talking about picking out all the different astrophysics, he was going in and actually saying, okay, there's a staining around them, which may be GFAP or this or that, and he's manually doing it.
Yeah.
And so he has got basically, and he doesn't have full sets of data, partial sets of data. But is there a way of using some of these techniques that you're using here that somebody like him could have used to then take some of the initial data set and then somehow come up with a way now to go back and then automate that identification?
Right. So I mean, the answer is definitely yes. Now let's take 20 seconds just to give an anecdote here. So I'm a colleague in Illinois in the Bioengineering department, and he was studying a cellular structure called crown structures in light sheet microscopy images. He had a postdoc who was manually going through and segmenting these crown structures in just terabytes of light sheet microscopy data. The postdoc for 6 months doing this.
Yeah.
They came to us. We put one of my grad students on it. She trained some networks. 2 weeks later. Because of his efforts in annotating all that data, 2 weeks later we have a fully trained automated method. Now in that lab they never have to do it again.
It seems to me like
it's the same thing.
rally him to
The same thing. And when I saw that, my immediate thought was that the same thing's going to happen here.
Okay, so we have, it has been very hard day for Mark. From 8 a.m. he has been here working with us. So let's thanks again for the. We have the award right now, but we have to move quickly to after the award ceremony to the fountain because we have this reception and they are waiting for us there. We have to complete it certain times. Okay, the first thing is the gift for.
Since you've spent such a long time during the day, there's something in this to remind you about all the coffee that you had. I know we haven't had a time to talk about the department, but here's all the information.
We have some gift present for the judges, but I don't think all of the judges are here, so we will give them. Some are here, so okay, so let's give some of the person where the.
Where are the presents?
Okay, so maybe I told them that we're going to give
Being here and spending it.
Then we have the award.
We have the award. Okay, please.
Also, I also want to make sure that I have, this morning we talked